Hello everyone, my name is Edgar. Good afternoon everyone. I'm currently studying a master's in telecommunications engineering, and today I'm going to present a project on behalf of all the team that is currently working on it, which is called the IEEE Open PocketQube Kit. My colleague yesterday explained a bit, presented the mission and the experiments and the payloads, and today I'm going to focus more on the platform itself and also the educational insights. Okay, first I'm going to start a bit about the origin of the project, then I'm going to explain about what is the project about. Then I will continue with the platform, all the subsystems and ground station and all an electric ground support equipment that we have designed for the PocketQube. And I will finish with educational insights and resources that we have developed for the project itself. First of all, what is the Open PocketQube Kit? It's an initiative proposed by Professor Adriano Camps. This initiative was proposed to the Institute of Electronics and Electrical Engineers, specifically the section of Geoscience and Remote Sensing Society. The main objective was to facilitate the entry barrier to institutions and universities to the space, and they decided, well, the Professor Adriano decided to create an open source kit for a PocketQube. The PocketQube kit contains basically 3 different PocketQubes with 3 different payloads. One with a BGA camera, which is the picture here. Then one with an L-band radiometer, which is this one here. And then the last one with a K-band radiometer, which is here. And then you have your option to create your own payload and include it in the PocketQube kit. Then, as for some educational activities and resources, I will explain them later, but well, here you've got some insights, some training courses that we have done and we will do, and some information. Well, as it is an open source kit, basically, we have everything in GitHub, and also we have developed a wiki and some videos that I will explain later. First of all, I'm going to start with the platform. Here you've got a render of the PocketQube itself. From the bottom, you can see the stack of the PCBs, starting from the ECS, then with the EPS, then with the OBC, and finally with the payload, in this case, the BGA camera. First of all, I'm going to start with the ECS. The ECS basically serves as an interface with the outer boards of the PocketQube and the main stack of the PCBs of the satellite. Here you've got the sensors that are featured in the PocketQube. First of all, a gyroscope, a magnetometer, photodiodes, and temperature sensors. These last 2 sensors are included in each outer board, and it is a requirement that the payload that, if someone wants to create one and include it in the kit, has to comply, because it's needed for the attitude determination of the satellite. And then, as actuators, we are using 3-axis actuators. These actuators are magnetorquers embedded in the outer boards of the satellite, as you can see in the picture. They are formed by planar helicoidal coils distributed in 4 different layers inside the PCB. And, well, in this picture you can see for the +1 magnetorquer, we cannot include it in the top board as there is the payload, and we have decided to include it in the inner layers of the satellite. Then, above the ECS, you can find the PCB of the electrical power supply. For the electrical power supply, I will start with the battery. As you already know, the battery has really low capacity. As you can see, 1,400 milliamperes per hour. Well, we cannot afford to put another one because of the size. The choice criteria that we followed for designing the electrical, for including the battery, is basically because of the energy efficiency. It's better, well, this battery works at 3.7 volts, and the PocketQube is working at 3 volts. It's better to reduce this voltage as it's more efficient, instead of maybe with a lower voltage, increase it until 3v3. Then, because of the PocketQube requirements, then following with the operational range, well, the temperature operational range, and finally with the mission objectives and lifespan. Then, for the solar cells, as in our case, the payloads consumes a relevant amount of battery, we have decided to include high efficiency solar cells with an efficiency of 30%. That means that the solar cells are the most expensive part of the kit, as it's a requirement that has to comply with for the payloads. Then, above the EPS, we can find the onboard computer PCB. This PCB shares also space with the communications subsystem. For the onboard computer, as for the power restrictions, we have decided to use the STM32L46R6 microcontroller. This is a lower consuming microcontroller, which is really important to use in a PocketQube. Then here you've got some specifications. The most relevant one is that for the flash memory we have only 1 megabyte. And then as for operating system, we are using FreeRTOS. And finally, these are the communication protocols that we're going to use in the satellite, starting from the I2C for the ADCS and the radio frequency payloads, then the UART to control the VGA camera, and the SPI to control the LoRa transceiver of the communications. Then, as I said, the communications PCB shares space with the onboard computer. For communicating, we have a quarter wavelength monopole antenna at 868 MHz frequency band, which is, as you already know, an ISM band, a radiometer band. And well, here we've got a challenge, which is basically that there's a regulation by the ITU which says that you cannot transmit more than 1% of the whole duty cycle of the transmission. And then, for the transmitted power, we are using 22 dBms. Here you've got a picture of the radiation pattern that we have computed in the anechoic chamber of the university. Well, obviously it's omnidirectional, but you have to check and characterize it. Then here you've got some specifications of the data budget. The average downlink bytes per passes are 12.5 kilobytes. And then, to finish, we have the 3 payloads. Mainly, I will focus on the educational purposes here. For the VGA camera, its main objective is for basically introducing the new people into the creation of a payload. It's very basic for learning the basics of everything. Mainly, you will learn about image acquisition and processing in space, and also it's a good opportunity to learn about task management in the STM32. And then both payloads, which are mainly, as our kit, it's sponsored by the IEEE Geoscience and Remote Sensing Society. We have decided to develop 2 radiometers to introduce the people to the world of remote sensing. Mainly, you will learn fundamentals of antenna, you will be introducing radio frequency interference techniques, and finally, you will learn the basics of payload design for Earth observation. Then, we have designed an electric ground super equipment in the lab. This ground super equipment serves, it can be used for, it's standardized for almost all 1P PocketQube. The only requirement is that you have to have the vertical connectors in each PCB. And here we were conducting a test with the electric ground support equipment. This test consisted of basically transmitting by a LoRa module and a picture taken, we transmitted a telecommand to the satellite, and this telecommand consisted on taking basically a picture with the VGA camera and then retransmitting it to the LoRa module and processing in basically the computer. Then for the ground segment, we have decided, we recommend to use basically a TinyJS network, taking advantage that we are using LoRa modulation, and it's very easy to implement one in the ground station. The advantage of using basically TinyJS is that you will have almost world coverage for the downlink if the TinyJS ground station antennas are compliant with the specifications of communications of your satellite. Then you will be able to have a real-time monitoring of the state of the satellite, as you will have more contacts, and it's much better to track the status of the satellite by this way. Then I will finish with the educational insights and resources that we have in the kit. First of all, a bit of introduction to the team. Well, we are at almost more than 70 students have participated during these 4 years of development. Now the current team is formed by 7 bachelor students, 4 master's students, and 1 PhD candidate. This team is the one that is currently working in the Fly Your Satellite mission, and with different backgrounds. And this is the information of the academic return that we have conducted for the mission, for the kit. Then, one of the key parts of the kit is that we have developed a wiki. This wiki contains the information from the scratch to the current state of the satellite. Here you've got the table of contents of what you can find, from the mission analysis until structure and information of every subsystems, functional tests, hardware design, software design, everything. Then all the information about the payloads, finishing with operations, how we will perform the operations, and then procedures of environmental test procedures, assembly procedures, and finishing with the federated satellite experiment. Then we have developed a course in the platform of Unite. The course is sponsored by IEEE, GRSS, UPC Unite. This course consists on 23 videos about small satellites and the open source PocketQube Kit. The part of small satellites is conducted by the Professor Adriano Camps and Professor Hugh Park. And then the part of the PocketQube Kit is developed by the current team. Here you've got also the QR, as before with the wiki, to take a look at that. Then, about the training sessions that we have conducted, well, this training session will be conducted on summer. It's part of the Barcelona International Youth Science Challenge. In these training sessions, professors, engineers, and the students of the team will take part teaching undergraduate students from around the world. For example, there's people from Kazakhstan that has presented to this course. That will, using the PocketQube Kit, will teach basically how to use the lab facilities, how to solder, how to conduct functional tests of each subsystem, and finally showing how to conduct environmental tests inside the clean room that we have in the lab. Then, this is the training session that we have done some months ago. This was for people from the Middle East and North Africa region. The professors from Tunisia, Oman, and Algeria came basically with some with some information about the videos. They watched the videos, they came here for us to resolve these doubts that they could have for the video, also to teach them easier the videos, and finally doing enhanced demonstrations of assembly and integration and verification activities of the PocketQube Kit. Then, finally, some weeks ago, some students from the 2 Korean universities, these 2, I don't know honestly the names, well, the course consisted on basically the same. As these people only could assist one day, we did a fast training course in which we teach them basically some functional tests with the electric ground support equipment. We did the test of transmitting the VGA camera, and then we finished the training course basically showing enhanced demonstration of thermal vacuum chamber and vibration test in the shaker. Well, this was my presentation. Don't hesitate to ask me, and if you have any doubt, please ask me. And here you've got all the QRs of the web pages and wiki and the videos. Thank you.